What's up, guys? It's LeetCoder. This is LeetCode Two Sum. Given an array of integers nums and an integer target, return indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. So example 1, nums is an array of 2, 7, 11, 15. Target is 9. So 2 and 7 summed up equals 9. So our output's going to be 0 and 1 for their indices. And in example 2, 2 plus 4 equals 6 here. So the output is 1 and 2. So let's think of a brute force solution to solve this. So let's use example 2. So 3, 2, 4 is our nums and target is 6. So all we have to do for the brute force solution is check each element with every other element in the array. And if those two elements summed up equals the target, we're done. So in this case, we check 3 and 2. They do not add up to 6. We check 3 and 4. They do not add up to 6. Then we check 2 and 4. Oh, they add up to 6, and we're done. So in this case, we're going to be checking every element in the array, and we're going to be checking every element with the worst case, every other element. Basically, we check n elements n times. So the time complexity is O of n squared, since it's n times n. Oh, that's a big parenthesis. There we go. And then the space complexity is, well, we're not really storing anything, maybe just the variables for the indices. So that's O of 1. So now, how do we improve upon this solution? Well, we ideally want to get to, let me draw this. We ideally want to get to an O of n solution. So the way I like to think about this is we can transfer some of the complexity from the time to some of the complexity in the space. So we can say, if we can get an O of n time complexity algorithm, maybe that'll require us to get an O of n space complexity algorithm. So if we think about this, instead of checking everything every single time, we can simply store what we've already seen into some data structure and use that data structure to figure out if we've come across the solution or not. So again, we have our array 3, 2, and 4. And we first start out with the first element, 3. And we say, okay, well, we haven't seen anything, so let's write this scene data structure here. So we haven't seen anything yet, so let's just add 3 to our scene, and that's it. Okay, then we go to 2, and we say, okay, is 4 an element in our scene? Because 2 plus 4 would equal 6, right? Oh, I didn't write the target. Let's write the target here. Because 2 plus 4 would equal 6. But no, there's no 4 in our scene data structure. So let's just add 2. Okay. So let's go to the next iteration. So now we're on 4. And we say, oh, well, there is a 2 in our scene data structure. Therefore, we already have the answer. And we need to return the indices. So now we can see, oh, well, we don't have the indices in our scene data structure here. So actually, when we're storing the numbers into our scene data structure, we need to also store their indices. So 3, it's the first element, so the index is 0. 2 is the second element, so the index is 1. So if we can store this, then when we reach the 4 here, we can say, okay, there's a 2 in this scene data structure. It has an index of 1, so therefore we're going to return 1, 2. Now, the question is, what kind of data structure is this? And if you've studied data structures, you'll know that this is a hash. So in Python, it'll be something like this with a comma here and like that. You know, it'll be equals. So this is a really common data structure used in a lot of these algorithms because it has O of 1 access time. meaning that you can access an element in this hash in O of 1 time. And of course, there are a couple assumptions there that allow you to do that. The assumption is you know which element you're trying to access ahead of time. So, for example, when you're on this 2, you know you're trying to access a 4 here. And when you're on this 4, you're trying to access a 2, because those would be the numbers that would add up to 6. The other assumption is that it doesn't matter if there are collisions or not, meaning it doesn't really matter if we have multiple 3s that we've seen in this original array. And the reason it doesn't matter is because of this assumption here. You may assume that each input would have exactly one solution. This basically means that we can just overwrite the value in this hash with whatever the index is of the most recently seen number. Because we're overwriting things, we don't have to worry about collisions. Then we can assume that we're going to have O of 1 access time. And therefore, because we're just going through the array once and we're just accessing a hash in O of 1 time, the overall time complexity is O of n. And because we're storing a hash that has up to n elements, the space complexity is O of n. Before we get to the code for this, if you found this helpful so far, please give a like and a subscribe because it really helps the YouTube algorithm. And with that said, let's get to the code. Okay, so here's the code for this problem. Let's think about this. We need to return some output. So we'll have output equal to an array. And like we said, we're going to have a scene hash. And I think that's it for our setup here. So let's go and now loop through for each num in nums. We're going to see if the value that we need is already in the scene hash. So I guess let's first store the value that we need. So we'll say val needed equals target minus num. So if val needed is in scene, then we simply return the index of scene at val needed alongside the current index. And actually, we don't have this value yet, but we'll come back to that in a second here. And then otherwise, we just need to add the current number into scene. So we'll say scene at num equals index. And that should be it. So actually, we don't even need this output because we're just returning here. So we can get rid of that. And the only other thing we need to do is get the index. So in Python, the way to do that is to do this. So enumerate basically just gives you the index as well as the individual element here. So let's run this code. And we can see that we got the correct answer here. And let's just, before submitting, I like to mentally think about one of the examples. So let's see. So let's go through the 3, 2, 4 example. So first our index is 0. Our num is 3. Our val needed is 3. 3 is not in scene, so we just add 3 with the index of 0. Next iteration, we have 2. So the val needed is 4. So 4 is not in scene, so we add 2 to the scene of index 1. And then the next iteration, the val needed is 2, because target minus 4 is 2. So then val needed 2 is in scene, so scene at 2 is 1, and index is 2. So that should work for example 2. So let's click submit here. And we can see we're all good here. And that's it. So really the thing to know is when you want to improve time complexity, you probably will need to worsen space complexity. But that is okay because space is cheap and time is not cheap. So it's almost always better to sacrifice some space complexity for time complexity. And with that said, if you liked this video, please give a like and a subscribe, and I'll see you next time.